Hello, we are Textron XY Move, and we are part of a joint effort between Georgia Institute of Technology and Textron Specialized Vehicles in Augusta, Georgia. Team members are Dongyeon Justin Yu, Mo Yang, Sungho Stephen Cho, Timothy Kyung, Yingxin Vincent Chu. At Textron Specialized Vehicles, engineers use MTS actuators to replicate various road terrains and conditions to test their products. These actuators, weighing nearly 550 pounds each, are moved into position manually. This not only wastes time, but is a tremendous safety hazard for the engineers moving the 4 posts into position. The solution proposed is an autonomous system capable of moving 4 MTS actuators into position and withstanding an additional 1,500-pound load added on top of each actuator. The main objective of this project is to provide a safe-to-use system while dealing with the 550-pound dynamic load and 2,000-pound static load. The actuators must be able to move 3 to 4 inches per minute, though an ideal speed would be up to 10 inches per minute. After movement, the actuators must be able to lock in place. The range of motion must be wide enough to encompass all models of Textron Specialized Vehicle products and be able to support the use of 3-wheeled vehicles along with 4-wheeled vehicles. Fulfilling these objectives will provide a quicker and safer means of moving the MTS actuators into position.
The final design has been improved upon the second conceptual design. The second conceptual design had incorporated a rack and pinion system for one axis and a wheel with tires on the brushless motor for the other axis. The idea of the rack and pinion was abandoned because it can only work with certain levels of friction. If the friction is too high, for example, due to the high load of the MTS actuator causing a large downward force, the mechanism will be subject to wear more than usual and will require more forces to operate. Due to the friction, it is under constant wear, possibly needing replacement after a certain time. In addition, the idea of a conventional wheel for axis traversal was also replaced to reduce the chance of slipping on the existing platform of the testing site. By incorporating the threaded rod and the nut system on the both upper and lower motion systems, one could reduce the height of the overall system as well as improve on manufacturability. Both systems for the X and Y axis have used the concept of the threaded rod being attached to a stepper motor. The final design relies on two independent stage mechanisms. The lower motion stage has a stepper motor that rotates the threaded rod, effectively traversing the upper subsystem on the steel rollers. The upper motion stage has the stepper motor rotating the thread rod that moves the MTS plate on ball transfers or casters. The stepper motors were utilized because, as compared to other types of motors, hybrid stepper motors have a larger stall torque while maintaining a high level of precision at the same time. In addition, stepper motors are useful because the angle of the rotation of the motor shaft, hence the movement of the thread rod, can be tracked by controlling the pulse signals generated by their respective motor controllers. This eliminates the necessity for end-stop switches or distance sensors because one can precisely monitor how much has been traversed across each axis. According to our calculations, a motor torque of 44.896 ons/inch is necessary to traverse the MTS actuator of the final design. Hence, the conventional NEMA 34 with a continuous torque of 15 ons/inch has been found suitable and was selected. The half-inch threaded rod that is used as a square thread form that is commonly used in high-load applications such as lead screws and jack screws. Although it is relatively costlier than threaded rods of the other form due to difficulty in fabrication, it is the lowest friction and most efficient thread form, and it gets its name from the square cross-section of the thread. Due to the lack of thread angle, there is no radial pressure on the nut of the moving platform with the MTS actuator, hence increasing the nut life. As stated in the project requirements, this positioning system must sustain 500 pounds while in motion and 2,000 pounds while static. In order to sustain this massive weight, 6 solid clear anodized aluminum single profile extrusions have been used with high capacity flange mounted ball rollers between the extrusions and the moving platform. These heavy duty ball rollers are shock absorbing, each furnished with a 1/4 inch thick neoprene mounting pad and a dual sealed ball and side vents to eliminate contaminants. 8 ball rollers, each capable of withstanding 150 pounds, that provide support of a total of 1,200 pounds, which is more than enough for our purposes. 3 T-slot extrusions are placed on both sides of the threaded rod and are fastened with brackets. Attached to the upper motion stage are 4 11-inch strong galvanized steel conveyor rollers that are used to traverse along the bottom platform. The spring-loaded axles enable easy replacements, and steel ball bearings on both sides of the roller cylinder allow frictionless traversal. These conveyor rollers are attached to custom manufactured roller brackets that can house 2 rollers per pair. The weight of the MTS actuator is first distributed between the 8 ball transfers between the MTS plate and the T-slot extrusions, and then the load here is subsequently distributed along 4 conveyor rollers. This eliminates any downward force acting directly onto the 2 threaded rods of both axes and prevents any stress or bending on them. With load distributed, our stepper motors can easily and precisely turn the threaded rods and traverse the MTS actuator to any desired position. In order to confirm the reliability of our system, a finite element analysis, or FEA, has been conducted on our design.
To provide a proof of concept of our design, a scaled-down model of the entire system was built using a scaling ratio of 1:3. Here you can see a picture of the finished product. Here, this slide shows how the MTS actuator can be moved in both the X and Y directions without interfering with each other with our concept. Upon evaluating the prototype, several pros and cons can be observed. Benefits of using this autonomous design include a friendly user interface, quick but safe and precise movement of the actuators, a cheap yet durable design, and a compact and modular system. Cons of this design include no coordinate system to base actuator movements on. The prototype is not fully autonomous because it lacks an automated locking function. No damping to deal with the vibrations of the MTS actuator, and limited range of motion due to the thickness of the aluminum T-slot extrusions used. Possible improvements for future work could include the addition of a coordinate system to be able to easier move the MTS actuators into position. This would not only increase the accuracy and precision of movement, but would also increase the user-friendliness of the system. It could also be possible to preload coordinates and settings for repetitive future use. Another improvement would be to include dampers within the system to deal with the vibrations from the MTS actuators.